Alrighty. Good morning, everyone. Welcome back to Math 154 as always. Week 10, Lecture 2, moving right along. So we know we have 4.3 and 4.4 due dates from the last lecture, November 2nd and November 4th, respectively. We will finish 5.1 and 5.2 today, so those will both be due on November 9th. I've been very nice and kept quizzes and discussion boards and Excel files kind of off of the docket right now with our midterm coming up. Not all teachers are so nice. A lot of teachers will still throw all the different types of assignments at you, so hopefully you can appreciate that. But as your basically final reminder, your midterm is going to be November 1st and November 2nd. Remember that TCC is technically closed on November 2nd, but because I'm giving you 2 days for a midterm instead of 1 day, I can still give you that day. It can just be taken as a sweet. I have an opportunity in case I can't take it on the 1st. 20 questions, 2 hours. That's one attempt only. Once you open the midterm, you cannot close it and come back to it. It is not like a regular homework assignment in that manner. You want to make sure that you're showing all your work on scrap paper. You want to make sure your name is on each piece of paper. You want to make sure that your work is numbered and neat. And then you will make sure that you submit it in Canvas within 15 minutes. Remember, the midterm is in my math lab. You will only see the midterm available on those 2 days. It will be the very top assignment. And then where you submit your work in Canvas will also only be visible those 2 days. And I'm going to show you what that looks like right now, just to be safe. You should have a good idea of how submission things look in Canvas, but even still. So when you're in your particular Math 154 shell, you will have, what is it at the top? Your lecture videos. There's something above that, like the day one stuff. Then the lecture videos, then I believe projects. And then before quizzes, you will now see, you will see the submit exam work here when it's available on November 1st and November 2nd. See, I have this little no sign instead of a green check mark. That means it's not visible to you yet. I will only have that visible again on November 1st and November 2nd. You can also see that's where you'll submit your final exam work. But again, no green check mark. Once we're talking about the final, that would be activated. Okay, so next class, I will be assigning another quiz. I will be assigning another Excel file, so be prepared for that. Remember that if you want to have a really, really good comprehensive review of material, you can find that in Canvas. So it's a little lower in that section. You should have already found that by now, hopefully. That's going to be about 3 times as long. It's a bigger bucket of questions and answers for you to look through. There's also the formula sheet there. And by formula sheet, remember, I'm just saying like 2 or 3 conversion formulas. Remember, you still have to know all the time formulas. 60 seconds is a minute, etc. You still have to know all the different formulas throughout the semester, like how to calculate a weighted average, how to go from an annual rate to a periodic rate, anything like that, calculating simple interest, etc., etc., etc. All right, so without further ado, let's pick up where we left off in 5.1 and then really quickly get into 5.2. So we're going to talk about that concept of a fixed amount and a variable amount and using that into in an equation and how we can put numbers in and get numbers out. So here we go.
We finished all of these notes. We had just talked about how linear equations can be expressed as a total amount being the sum of a variable amount, which means an amount that changes. That's what the word variable means. It varies. And a fixed amount, which is an amount that doesn't change. So if you wanted to break down, the amount it costs for you to live in your home each month in a very simple way, you could say you have the rent portion or mortgage portion, which is typically a fixed amount that doesn't change from year to year. Well, rent might go up every year, but your mortgage wouldn't. And then you have your variable amount, which would be things like your electric bill, your water bill, that would depend on how much electricity you used or how much water you used. Now, in the real world, your electricity and water, they're not a linear rate, unfortunately, but they can be approximated as one. But that's something that we're going to get into over the next several chapters, how a mathematical model will be good for one amount of time or one kind of range of values, but eventually it kind of falls apart. And that's not true of all models, but when we try and model things like population size, any financial dynamics, eventually these models kind of fall apart. The same can be said of trying to model a population with a disease count. You know, that might be relevant for right now. A lot of people will say, oh, well, it's exponential growth. And that is true for a short period of time, but eventually it becomes something known as logistical growth, which we won't actually study in here. And that's because there's a ceiling as to how many people can get sick. Anyways, I'm rambling. Let's get back to the simple concepts. We're starting at the basics. Total amount is a variable amount plus a fixed amount, which we said the variable amount has to have a variable. So it's usually something like total equals 5x plus 3. I think I gave similar numbers last time, maybe 3x plus 5, where 3 would be your fixed amount. So that's like your mortgage. And then 5, that's saying that for every single x, you're paying 5 of something. So if x is 1, you're paying $5 or cents for the first one. If you have x is 2, you'd be paying 10. If x was 3, you'd be paying 15. So this is the variable amount. And when you're dealing with real world context, the variable amount usually has the word per in it. So the variable amount usually has the word per. So it'd be like $5 per ticket. So it's not saying you just pay $5 no matter what. It's based on the number of tickets. It's an independent-dependent relationship. So what we want to do is we want to take this idea of being able to write equations for our models, and we're going to go back to the 3 or 4 problems we did last time where we graphed them, and now we're going to actually write out their equations. And you can use words, you can use letters, you can always use y and x if you really like, but I'm going to try and stick to letters that are a little more relevant for the problem. So again, what I'm referring to is we made these 3 graphs. We did a graph for the weight of water based on with the bucket and without the bucket in that opposite order. We did buying tickets at a fair or Busch Gardens or something where we had the $15 flat fee to get in and then $2 per ticket. So we had a graph without the flat fee and then with. And then the same thing for a driving distance. So if you have not seen that yet, that means you need to go and watch last class's lecture. So this is what we're getting to now. Zoom in just a little bit. There we go. So blah, 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 blah. Constant of proportionality is a rate. That's something that we have discussed before. A constant of proportionality is a rate. This is what, back when we were talking about that y equals kx stuff, k was the constant of proportionality. And that was always, it would always have a per in it. So 5 per 1, $5 per 1 ticket, something like that. So going back to the previous problems, the cell phone problem in particular is what we're looking at here, where we had 2 cases. We said, all right, one plan was 5 cents per minute, another plan was 7 cents per minute. So we could say the cost in cents for the first one is 5 times the number of minutes, which we could use the letter M to clearly represent minutes. Or for the 7 cents per minute plan, that cost would be 7 cents per minute. But this was not the total cost. That was just the proportional part. That was the part without the fixed amount. So again, the fixed amount, this adding of a number, makes something no longer proportional. It still has some similarities, which we talked about being the slope, which we'll talk about in more detail in 5.2. But it doesn't go through the origin anymore. You can't just say as one doubles, the other doubles. It doesn't quite work the same. So what's going on with that 20? Well, that's when we took the $20 monthly fee. Now we're only doing this one, at least for now. Yeah, no, we're only doing this one with the 5 cents per minute plan. So we're not going to do the 7 cents per minute plan with the full cost, including that hidden fee, which is not technically hidden. We're seeing it right in front of our face. So this 0.05 M is the same thing as this, except now our cost is in dollars. These 2 things are the same. It's just one is in cents and the other is in dollars. But then this is a total cost. So we're adding in that fixed fee, that flat fee we pay every month of the $20. So this 0.05 M, that's our variable amount, and then the 20 is our fixed amount. And as always, our variable amount needs a variable next to it. So this is our goal for the next 3 problems. We want to be able to write something like this or like this. Now, they say this is not proportional, again, because of the 20. We've already discussed that. It's similar but not the same. This model uses C and M, so things are very clearly labeled. Also, this is a perfectly fine model, or directly above it, it uses words. Now, in my math lab, if you're typing in the model, they're probably going to want you to just use the letters. But then you have a third version of it down here with, instead of C and M, Y and X. So this is perfectly fine, but unfortunately, what you would need to do is really write down that X is the number of minutes and Y is the cost in dollars. If you just write it this way, your variables are not labeled, you don't know exactly what it relates to, it's not very clear. At least by using C and M, there are hints as to what they are, but I would still love it if someone didn't write all of this part, if someone wrote somewhere that this C is the cost in dollars and that M was the minutes. I know it feels less necessary, but you never know what'll happen when you want to look at your notes a year from now or 2 years from now, and all you see is C equals 0.05 M plus 20, and you go, well, what the heck was M? What was C? I don't even know. All right, so I got to clear my screen. Let's go off of annotate. So we already did the first one. Don't worry about this little sub 2. We're not going to do any of that. I don't even know why that's there, but it's okay. If they were going to call that 2, they should have called this a 1. That's all I mean. So for problems 2, 3, and 4, this is our goal, 2 parts, A and B. 1, we're only going to write the proportional part, which is only the variable amount. So this is not including the fixed amount. The cost is the 5 cents times the number of minutes. But then for part B, we add in the fixed amount for whatever the problem was. So that's what we'll be doing for questions 2, 3, and 4. Can I get all these on the screen at once? Perfect. All right. The weight of water is proportional to the volume at a rate of 8 pounds per gallon. Write an equation for this proportional relationship. We're ignoring the bucket. The bucket doesn't exist. We're only worrying about the weight of the water. 8 pounds per gallon. So the weight is proportional to blah, 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 blah. So that says we should write something like weight equals. So the weight of the water is means equals, and then proportional, that's where you have your y, your kx, or whatever number and letter or word you want to use. But the rate is 8 pounds per gallon. So for every 1 gallon, you would have 8 pounds of weight. So that 8 is the k. This 8 is the k. Now, maybe it's 1/8. If you had this solved for the the volume instead, it would be 1/8, but that's why I said to make sure we're doing this in an appropriate way. And you can always check this at the end. You can plug in some numbers and see if everything makes sense. So 8 times, so that's weight equals 8 times the gallons. Gallons is a type of volume. If you wrote weight equals 8 times gallons, that's okay, but I might prefer something like pounds equals 8 times gallons, because then they're both talking about units and not one is a label and the other is units. Or you could just go W equals 8V, as long as you establish somewhere that W is weight and V is volume. So what you can do is you can use this equation and go back to that table before, and I'm not going to be able to do that because I'd have to erase everything and move, and it's just time consuming. That table, we had something like 0, 0.5 is 4, 1 is 8, 1.5 is 12, and you could plug in any of these volumes and you should get the weight. So if you plugged in a half, 8 times a half is 4, and you get the right thing. If you plug in 1, 8 times 1 is 8, and you get the right answer. If you plug in 1.5, 1.5 times 8 is 12, and you get the right answer. It works. Part B, now we're going to assume that we have that bucket. So we're talking about the weight we're actually holding, and that bucket weighs 10 pounds. So we said all we do is just have this be the fixed amount, and we add it to the variable amount. So now our weight is 8V. There's the variable amount based on the water itself, and then we add the bucket, which is always 10 pounds no matter what. See, the bucket doesn't change weights. It's the water that changes weight. Or if you prefer, weight equals 8 times volume plus 10. Again, use your words, use your letters, whichever you're more comfortable with on your own. My math lab, you're probably going to need to use letters. They may tell you to use Y and X. They may not. You just have to pay attention. All right. Next up, let's make the next equation. Sorry about that. The cost is proportional to the number of tickets you buy at the fair at a rate of $2 per ticket. So the cost is blah, 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 blah. So we go cost equals, and it's proportional. So the next thing is just going to be a number times a variable. And the number is, I think, very clearly the $2 per ticket. That's the per, so that's the thing that goes in front of your variable. And then per ticket, so 2 times the number of tickets. It doesn't say 2 tickets, it says 2 times the number of tickets. Or you could just go C equals 2t, or you could go Y equals 2x, but you have to write what X and Y are in that last one. If you want to use Y and X, you absolutely need to label them. Otherwise, I'm going to go, well, which is which? You didn't tell me. Now, when we account for the fact that we had that $15 flat fee to get in, but that's fixed, so that's not going to be multiplied by anything. This does not depend on some other amount. So now it's cost equals 2 times the number of tickets. I don't know why I just did it. That, there we go. And then plus the 15. That's all it is. Or C equals 2t plus 15. It's nothing super crazy, but as always, if you don't practice it first, you're not going to know what to do. You need to see it executed. You need to try it yourself. You need to practice it 3, 4, 20 times until you get used to it. It's just like anything in life. You're not going to be amazing at it the first try in general. Some people will get lucky and they are. Most of us have to practice things. All right. Finally, that driving distance. So the distance you drive is proportional to the time driving at a constant speed of 40 miles per hour. Now, honestly, you don't have to be told everything so blatantly mathematically. You don't have to, the distance you drive is proportional to the time driving. Someone could just say you're driving 40 miles an hour, and that's implying that your speed isn't changing. 40 miles per hour, that word per is a massive clue that it's a proportional relationship. Again, just that part, not accounting for the 100 extra miles, just in this parameter only. Per is a clue that that's a y equals kx kind of setup. So you go, okay, well, we're talking about distance and time. We usually are much more interested in going distance equals, I'm saying usually, but not always. And the phrasing of this does imply that we want to go distance equals blah, 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 blah. All right, well, 40 is our multiplier, 40 miles per hour. And then you could go times time again, if you like here. And if you don't trust this, if you think maybe it was supposed to be time equals distance times 40, then plug a number in and see if it makes sense. So plug in 1. If you go 1 hour, would it make sense that you go 40 miles? If you go 40 times 1, you get 40 miles. Well, yes, because your speed is 40 miles per hour. So 1 hour should get you 40 miles. And again, the abbreviated version, D equals 40t, would also work. Then we assume that we have that 100 miles we already drove. That's not going to be affected by our speed at all. That's a fixed amount. So we just go D equals 40t plus 100, or distance equals 40 times time plus 100. And again, you can always label things in terms of units. You could write that T is in hours and D is in miles. But that would also be true with different units as well, but you just have to be careful in how you make your assumptions. But again, I think a lot of people might want to actually label their units. That was weird. I hit mute for a second to cough, and then I couldn't unmute it because of my annotate. All right. Always something. Clear. Off. All right, there we go. Now, I'm going to do another one of my reminders. Also, I'm basically letting you know what the next Excel file is with this, that almost every Excel file from this course has a little preview in your guided worksheets. I know we've talked about this before, but I know a lot of people need reminders of stuff too with so many different things going on in this class. So here's a picture that might help you know whether you got your graph right or wrong when you go to do this assignment, because a lot of people end up having an extra line in this or one less line than what's necessary. So you've got something to compare and contrast to. So just remember that. So yeah, FYI, this is going to be our next Excel homework 4.1 lines. But I'm not giving you a due date yet because I want you focusing on the test, the midterm. All right, so that's that for that. 5.2. Slopes and Y intercept. So you've already heard me say that word slope many times already. We talked about that rise and run concept, but we're just going to lay it out in full detail now. So slope is the measure of the steepness of a line. Slope is the measure of the steepness of a line. So if you have, here's a line over here, let's put our axes. Let's say we got a point at this height right here, and then the line just kind of keeps going up from there. And let's just pretend like this number here is 12. And then as you move along this line, you're going right and then up, right and then up, right and then up, right and then up. Let's say you're going to go right 5 and then up 1. You'll go right 5 and then up 1 again to get to another point. Then you can go right 5 and up 1 to get to another point, et cetera, et cetera, et cetera. The 5 in this scenario is what we would call the run, and the 1 in this scenario is what we would call the rise. Rise is how far up or down you go. Run is how far right you go. There is no left. There is no left. There is no left. Say it with me. There is no left. There is only right, up, and down. We are only ever going to be considering ourselves moving right with these problems. We're talking about slope. Slope is rise over run. Slope is a rate. Slope is a rate. It's a rate of change, in fact. The word rate. I feel like we've heard that at least once in this class, right? You're darn right we have. Rate means ratio. It means fraction. And look at this. This formula has got a fraction in it. So slope is a rate. It's a fraction of something. Something on top of something. Well, what are the tops and bottoms? It's a rate of change. Change, as we were talking about in the last two sections of chapter 4, well, there was two types of change. We had total change and percent change. But if you don't throw the word percent in there, change is assumed to be a difference. Change is a subtraction. It's specifically new minus old. So if you have 2 points on a line, x1, y1, and x2, y2, your slope is calculated by the change in the height. So the change in the y values, how far up or down you go. So these are your y values. So that's your top. And then 2 minus 1 would be new minus old. And then the change of the x values would be the difference of these. And again, new minus old, the second minus the first, and that's this. A lot of people like to say, oh man, the slope formula, that's a pain to memorize because it's got these little numbers in there. It's a fraction, it's subtractions. What order do I do things? Do I do the x's on top, the y's on top? I don't know. Remember that slope is the rate of change. Remember, I try and suggest to not just memorize blatant formulas, but concepts. The concept here is that slope is a rate of change. Rate means fraction, change means subtraction. So we're going to have subtractions in the top and bottom. What is the rate of change specifically? It's rise over run. Rise implies height. height is y values, run is how far we go right, right is x values. So it's supposed to be the vertical change divided by the horizontal change, which is why we go y2 minus y1 over x2 minus x1. I don't care how you memorize that formula, but you have got to memorize that formula. We are going to be using that over and over and over and over and over. If you blatantly memorize it like an algebra student, that's fine. If you understand the concept and the definition of slope and what it truly means, that's the quantitative student approach. Rate of change, rise over run. Pairing those things together spits out the formula instantly. Now, there is another definition up here that I did not talk about immediately, but that's for a reason. The y-intercept. This is going to be very true in this course. Can be. And it's not always going to make sense. Your y-intercept can often be interpreted as a starting value or a fixed value. Those are interchangeable concepts. So you might think about what do we have at time 0 when nothing happens? Or what do we have when we talk no minutes? What's that flat fee we pay, that $20 that we paid for the 5 cents a minute plan? So a y-intercept can be interpreted as a starting value or a fixed value, one or the other. It just depends on the concept, whether you want to consider it as a fixed or starting value. Now, please note that I said, and this is going to come up, we will discuss when it makes sense and when it doesn't make sense. But in applications, the starting value does not always make sense. I'm going to go ahead and tie this in a little bit. I was just talking about earlier how some mathematical models only work for a while. Eventually, they fall apart. When they start falling apart, that's when y-intercepts start. Let me rephrase that. When they start falling apart, that's when y-intercepts tend to stop making sense. And again, we will see this in great detail through guided activities, just not today. So y-intercept, starting value or fixed value. So if you go back to those previous problems, we can talk about how some of those things are the y-intercepts. So a y-intercept as a point, so we always talk about x comma y. The y-intercept is always 0 comma something. So that's not a hashtag, that's the number symbol. Your y-intercept is always 0 comma something. Why 0 comma something? Because anywhere along this y-axis, you're not moving left or right, so your x value is 0. This point right here would be 0 comma 12 because you go left or right, 0 and up 12. Up here, maybe this is a height of 20, that would be 0 comma 20. Maybe down here, this is a height of negative 5 million, that would be 0 comma negative 5 million. We're not going to study intercepts as extensively as we would in a traditional algebra class. We're more worried about intercepts being the starting or fixed values, but we still do have to understand the basic traditional sense as well. So what I'd like to do is, and this last line just relates to what we just said, y-intercepts can be found by setting x equals 0. And when I say x, I just mean your input variable. If you're using letters like m for minutes, then you let m be 0. If you're using the letter like t for time, that's your input, then you let t be 0. So the initial time, or talking no minutes, gives you your fixed amount. So if I had, let's say I gave you a graph. And on this graph, we had this point right here, which will be 1 comma 6. And then we have this point over here. Let's have that be a 10 on the x-axis. And let's have this be an 8 on the y-axis. So I can say these 2 points form a line. Now, if we're doing an application, that's bad. If we're doing an application, we usually don't go, geez, I can't make a straight line. I can't talk and do that at the same time, clearly. If we're doing an application, this is usually how we make our lines. Because in applications, it usually, or quite often, doesn't make sense to go into negative x values. Like we can't talk a negative number of minutes. We can't drive for a negative number of hours. We can't buy a negative number of tickets. So again, in applications, this is usually how we make our lines. But if we're talking about just a pure math problem, no real application to it, then we do tend to extend that line in both directions. All right, so I have established here that this point right here is 1, 6, because we go right 1 and up 6. This point right here is 10, 8. Now, if you need to label these as x1s and y1s and x2s and y2s, remember the first spot is always an x value. The second spot is always a y value. And then you can decide which one are the 1s and 2s as long as you're consistent. I can't make what I'm about to do is wrong. I can't do this. I can't call that a 1 and that a 2. I have to be consistent. If I call the x1, the y is y1, which would force this to be x2 and y2. But I am completely free to swap the 1s and the 2s here. I can call the first point the old and the second one the new. Usually we go from left to right, but it wouldn't get you an incorrect slope because the math would fix everything. So then you can just go m equals y2 minus y1, the difference of the y's, 8 minus 6, over the difference of the x's, again, be consistent in order, 10 minus 1. 8 minus 6 is 2, 10 minus 1 is 9, and that slope is 2/9. What that says is, if you have one point, let's pretend I don't have this point for just a second. I don't have that point. But having this point 1, 6 and the slope of 2/9, the 2 is the rise and the 9 is the run. The run tells you how far right to go. The rise tells you how far up or down to go, up if positive, down if negative. So we go right 9 from 1 to 10. So that's me going right 9. And then we go up 2 from 6 to 8, and we get our point. Ignore the fact that I drew that just a little off because I was hiding it, but that was going up 2, up 2, right 9 up 2, and then from 10, 8, I could go right 9 and up 2. I can go right 9 and up 2. That's the idea of proportionality, but not actually being proportional. We're not saying as one doubles, the other doubles, but we are saying as one has a consistent change, the other has a consistent change. So that's why they're kind of cousins, if you will. Now, we've said several times already that if this line went through the origin, if for some reason you have a line that does start here where the axes cross, this would be proportional, but that's not what we had this time. And it's usually not what we have, in all honesty. It's pretty rare. There's usually a fixed cost somewhere. All right. Slope-intercept form, which you've already seen and you just didn't know it. Y equals mx plus b. This slope-intercept form is the exact same as a standard linear model. This is still a standard linear model. This mx right here, that is your variable amount. And the b here is your fixed amount. It's just variable amount plus fixed amount. It's literally nothing different from the last section. But the letters are a little more specific. They're a little more traditional for an algebra concept. Do you have to use these exact letters? No. You can use C equals and blah, blah, blah with an M instead of an X. The M and the B will end up being numbers, though. That's the point here. The M and the B should be numbers that you can either find or are given. So like y equals 0.05 x plus 20. That would be the same thing as C equals 0.05 m plus 20. That was the equation we had in the last section for cost equals 5 cents a minute plus the $20 in a fixed flat fee. slope-intercept form is very, 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 very awesome because the b, the fixed amount, is always right here. This point is whatever the b is. It's always on the y-axis. We call a y-intercept that because it's intercepting or intersecting the y-axis. Those two words are synonymous for a reason. Intercept, intersect. So wherever your line crosses your y-axis, that is whatever this number is. Then the m just tells you how far right and up to go, or how far right and down to go to get a second point. So you don't have to plug in a bunch of different x values to get this point and then this point. You can just plot your fixed amount as that height of b. Then you can use the slope and run and rise, or run and fall, as like some people like to say if it's negative, and you can get your next point. It's pretty simple with practice. And then just at the end of the day, one last thing to say before we move on to the guided activity. Actually, I take that back. We're not going to do the guided activity yet. We're going to do a couple more examples. Is that if you know the slope of a line in any coordinate, you can plug these three numbers in and find b, which would be the y-intercept, and then you've got your model completely. What I'm saying is if I tell you a point and a slope, you can plug them into this right here, figure out what b is, and then you've got your model forever and ever and ever. Now, some people might say, well, Mr. Beckner, don't you need the y minus y1 equals m times x minus x1? Sure, you can do it that way. If this was a traditional algebra class, that's the way to do it. If you still remember that way, you can do it that way, but I'm not teaching it that way because it's not really a quantitative reasoning way of doing things. We're just trying to stick to one idea, this variable amount plus fixed amount, and take that one idea and use it in as many ways as possible, just like we were doing with proportions, just like we were doing with other things in chapter 3 and 4. All right, so, oh, I don't have the example type. That's what threw me off, but I know what it is. Line, why am I bolded? Line goes through the point, 1, 12, a slope of 4. Find the equation of the line. This example right here relates to what I just talked about here. The slope-intercept form, along with, if you know a point and a slope, you can find everything else. Now, points always go x comma y. This is an x and a y. Now, you can label them little ones if you want to, but you don't really have to because they told us the slope is 4. Now, if we were doing that more algebra way of y minus y1, blah, 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 I would label them with ones, but I'm teaching this the QR way. And again, if you know the more traditional algebra way and it works for you, use it. The slope is 4. We said that for some reason, some mathematician decided that the slope should be the letter m. I know that the word slope does not start with the letter m. Maybe the Greek word for slope does. I'm not actually positive on that, but we just use slope being the letter m. Just accept it. Now, what this also means is I could say, all right, when x is 1, y is 12. That's one thing I could say. And then I could say that, if x and y had some concept like x is a number of tickets and y is a cost, then I could say that every ticket costs $4, or tickets are $4 per ticket. That would tell me the slope. Even though I didn't use the word slope, it tells me the slope because it's a per, and per is slope. Anything that's per is your variable amount, and your variable amount is slope. They're all one and the same. So all we're going to do is plug these three numbers into this where it looks like they would go. So instead of y equals mx plus b, the y is the 12 equals, the m is the 4 times, the x is the 1 plus, the b is the, well, what's the b? Well, I didn't tell you that, did I? Leave it that way. Honestly, if you don't want to use the letter b, don't use the letter b. If you want to use the letter f for fixed amount, hey, that would be cool. I'm perfectly fine with that. But what we got to do here is solve for b. Well, 4 times 1 is 4, so that's 12 equals 4 plus b. I really hope you know how to do your algebra to solve this. I'm kind of scared if you don't. Subtracting 4 on both sides, 12 minus 4 is 8. So we get 8 equals b. This is not done. Some people will just box this up and ship this out, and then they get a big fat error, x, whatever. It is true that 8 is b, but it's not the answer. They said to write the equation of the line. We need to write something like this, but with numbers in place of the m and b, and we leave the y and the x alone. You might be saying, well, Mr. Beckner, why don't you leave the x as a 1 and the y as a 12? Why don't you do this? Some student would think this is the answer. 12 equals 4 times 1 plus 8. Some people would think this is the answer. Okay, sure, 4 plus 8 is 12. That's true, but this is not a model. This is not a model. This is not an equation. There's no variables in here. This doesn't show you any type of relationship between two things. So that's not what you're supposed to do. What you're supposed to do is let the y and the x, or the c and the m, or the d and the t, whatever letters you're using, let them be them so they're allowed to change. So we go y equals 4x plus 8. This is the answer. And you can see that you have your variable amount, that's your 4 per, and here's your fixed amount, the amount that you pay no matter what if this was a cost. If these were costs, I would want to write somewhere that y is cost and x is some number of units, number of tickets, number of something. When I ask for an equation of a line, this is what I'm talking about. Y equals 4x plus 8, y equals 3x minus 7, y equals 1/2 x plus a million, y equals 20x if there is no fixed amount. Some equations of the lines don't have fixed amounts. They usually do, but not all do. So again, I don't have to give everything this way. This problem would relate to, hey, you've got a fixed amount of $8, that's your fee to get in, and you're paying $4 per ticket. That would literally be the same exact model. But this wasn't phrased exactly the same way. They didn't give us the initial amount. They gave us some random amount. This is not an initial amount. This is saying when there's one ticket bought, it costs you $12. But the cool thing is, you can create an equation that ends up giving you the initial amount out of that. That is extremely handy. Because now what we can do is we can graph this quite simply. All I'm going to do is use the information in the blue here. I'm going to ignore the point of 1, 12. In fact, if I do things right, I'll end up picking it up coincidentally. All right. X, Y. So this 8, this is the Y intercept, or the initial amount, or the fixed amount, which says on the y-axis there's an 8 somewhere. Let's make it about here. There's our first point. If you don't trust that, if you plugged in x equals 0, 4 times 0 is 0, 0 plus 8 is 8. So when x equals 0, you're going left or right, nothing. You go up 8. Now from that point, what you can do is you can use the slope to find another one. Sure, yes, they did give us 1, 12, so you could write 1 up 12 and then connect them. That is absolutely fine. But let's say maybe they didn't give us this information. Maybe they didn't give us this information. They told us the initial amount and the variable amount, and we got to graph the line with that method. Now, you certainly could plug in any other x number you like, 2, 3, 5, and see what the y value is, make a point and plot it. But what we can do is, with the slope being 4, well, that's not actually good enough because we need to see the rise and the run. This feels weird, but when we want to plot a second point using the slope, we actually want to write it as a fraction if it's not 1. Because that way we can see that the run is 1. So that says we're going to go right 1 from any initial point, and the rise is 4. Because it's positive, we'll go up. So from this point, we're going to go right 1 and up 4. Now, if If I go right 1, we started at x equals 0, so we end up at 1. If I started at 8 and we go up 4, 9, 10, 11, 12. Sorry, they're not spaced perfectly. I'm not going to correct that. And there's our second point, and then you can connect the lines and extend. Let's assume that this is a model, so negative x's don't matter. And there we go. And again, look at this. That point that we picked up was just coincidentally 1, 12. So you're thinking, well, Mr. Beckner, I shouldn't do it that way because it's more work. Again, maybe you weren't given the 1, 12. Well, Mr. Beckner, couldn't I just plug in whatever x number I like and find whatever y value it corresponds to? Sure. If you plugged in 1, 4 times 1 is 4, 4 plus 8 is 12. Boom, there you go. Or you could plug in 2. 2 times 4 is 8, 8 plus 8 is 16. So that point would be 2, 16. And guess what? From this point 1, 12, if you went right 1 and up 4, you would end up at 2, 16. If you plugged in x equals 3, you'll get 20. If you go right 1 and up 4 from 2, 16, you'll end up at 3, 20. Then 4, 24, 5, 28, 6, 32, 7, 36. That pattern will continue. And you can keep railing through them a lot quicker with that pattern established. All right, before we get to the guided activity, ignore this for a second, much longer than a second, in fact. Let's make sure we understand the difference of positive and negative slopes as well as zero slopes. So let's just put the 3 basic scenarios. We don't get into vertical lines in here, thankfully, which would be an undefined slope, FYI. Let's have a line that looks like this. Sorry about the squirreliness of it. A line that looks like this, and then a line that looks like this. This first example, as we go right, we go up. So that's a literal rise, which means your slope is positive. So m is greater than 0, that says your slope is positive. Here, all we ever do is just go right. We never go up or down. If we don't go up or down, that means that the rise is 0, and 0 divided by anything is, that's right, 0. Horizontal lines have a slope of 0. That's perfectly fine to see. So in fact, your equation would just be a number. It would be like y equals 5, y equals 7, y equals 40. Because if the m is 0, going back to this wouldn't be here at all, and you just get y equals your starting amount. So this is like you just pay $20 for your cell phone plan, and you're not paying 5 cents per minute. There is no variable amount. You just pay the $20 flat fee. So that graph would actually be a horizontal line with a height of 20. It wouldn't matter how many minutes you talk if you're only paying the flat fee. And finally, this one, as we go right, remember we're always moving right, this one goes down instead, which says that this is a negative slope. I'm just doing it in a different color to establish that point. No particular reason besides that. All right. What time we got? About 20 minutes. I think that will be enough. Okay. All right. Can I highlight on the screen? It's not really a highlight that's covering it. Pretend I highlighted this. Just pretend I highlighted that. This is going to be used in several of the guided activities. This is used at least once in the homework. And I could throw it on the final. I don't think that I usually do. Like I said, I try to be honest about what's on something. But this right here is an important concept. This is something that you can use in the real world all the time. Just like when we were talking about that cell phone plan, but we can be very methodical with our phrasing. Now, these little sideways arrows that look like less thans and greater thans, these are just saying you put a word in its place, whatever is relevant, or a number, whatever is relevant. So the output is changing by, so the output is the thing that the Y is. So when we were talking about our cell phone plan, the output was the cost. That's what the Y related to. So output, again, that's kind of like what the Y is if you're using traditional X's and Y's. Then you use the phrase is changing by. You could also use words like increasing or decreasing, whichever is relevant, by. Then the slope, that just means you're going to put a number. The Y units per X units. So this right here is just talking about something like miles per hour, or cost per ticket. Remember, the word per is your slope. So this is just saying the number with its appropriate units, because we're not just going to say the slope is 5. We're going to say that this thing that we're talking about is changing by this many units for that many units. So it's changing by 5 cents per minute we talk, or the cost is increasing by $2 per ticket we buy. This right here is what we call a cookie cutter. It is an exact phrase that you're going to use, but you have to practice with it. I know I am a broken record. Practice makes perfect. The wording seems very weird at first, but after you do a dozen of them, it's not so bad. Don't worry about this notation. We really don't see this anywhere else in the course. This is called a delta. It just represents change, as they indicate here. So again, this sentence right here is relating to that cell phone plan earlier. The cost is changing, or we could have said the cost is increasing by 5 cents per minute, or $0.05 per minute. Because every extra minute we talked, we paid 5 more cents. Okay, so let's try it out. Oops. Back on annotate, clear, off, scroll. Okay. This worksheet asks you to interpret slopes as rates of change using the sentence template as we already described previously. So the output, the Y, whatever that is changing by, or is increasing by, or is decreasing by. Write the number for the slope, then the ratio of those two units. But it has to be the output to the input units. So here's the graph of our monthly cell phone plan bill, whatever phrase you want to say for that, which we have seen before. It stops at 300 minutes. It doesn't go to 400 minutes, but that's perfectly fine. And this includes the variable amount, and it includes the fixed amount. So we can see our fixed amount here. When we don't talk at all, we pay $20. And then the run and the rise demonstrates the slope of 0.05. So every time you go right 1, you're going to go up 0.05. But this is me actually showing right 100 and up 5, which is the same ratio if you were to reduce it. But that's not what we're supposed to be describing here. We've already done all that stuff. We're trying to interpret the slope of the equation in real world terms using this cookie cutter template. So we say all right, the output. What exactly is the output? You might say dollars. The output's dollars because that's what Y is measured in. Well, Y is measured in dollars, but that's not the output. That's how it's measured. The output is the cost. Now, some might say cost, some might say total cost. I like total cost because that really implies it accounts for the variable and fixed amount. So the total cost is changing by, that's the next part of the template. Or if you didn't want to say it's changing by, you could say, well, it's increasing, so it's increasing by. Then the next thing is the slope, the value of the slope which is the number paired with the variable. That's the variable amount, 0.05. And then you just write the apples per orange, miles per hour, whatever that is. So what are we talking about? We're talking about dollars per minute. Dollars is the Y output, minutes is the X input. So we're going to say by 0.05 dollars per minute. If you prefer, if you wanted to talk in cents, then you could say we're increasing by 5 cents per minute. 5% would not be a great way of saying this because of the 20. So we can't really say that we're increasing by 5%. The fact that cents relates to 100 makes it feel like you could, but we do need to strictly use those units. So that's a good idea, but it's not exactly the same. Now, if there was no fixed amount, we could say 5%, but again, the point of this activity is to use the specific units they give you. So it wouldn't work for those two reasons. It's a good idea, but it's not perfect execution. All right, so there's our cookie cutter template. The total cost is increasing by 5 cents per minute or $0.05 per minute. If you wanted to do this in hours, you'd have to convert these numbers to hours by using dimensional analysis. It wouldn't be the end of the world, but it would be more time, and we're trying to avoid that. All right, so in the 6 or 7 minutes we have left, let's try and knock out these other two. Now, what I could have done is I could have given you that sentence and then asked you, and as well as the fixed amount, and then you could come up with the equation, you could graph it. You can go either way. I can give you the equation and the graph and ask for the sentence, or I can give you this sentence. I also have to tell you the fixed amount, and then you can build the equation and the graph. All right, let me see if I can get both of these on screen at the same time. Okay, good enough. So the concentration of pollutants. So this is basically saying at time 0 days, there's a spill in some lake or river somewhere, whatever. And over time, the pollutant dissipates into the air, the water. So this is showing that it's dissipating, it's going down over time. So this 100 would be the initial amount of the pollutant, and this minus 0.8, that's how much we're losing per day since we're measuring in days. So when we go to make our sentence, we can say that the output, which is the pollution, we could say the pollution, we could say the concentration of pollution, or we could just say the concentration, since, well, it did actually say pollutants. I know I'm hiding that word on my screen, but it does say pollutants. So the concentration or the concentration of pollutants, pollutions, however you wanted to phrase it, is changing by, or since it's negative, we can be more specific and say is decreasing by. Now, since I used the word decreasing, if I said changing, I would use the negative, but decreasing implies negative, so I'm not going to write the negative. I'm just going to write 0.8. And then we write the ratio of the different units. The different units are the parts per million and the days, and it goes the Y value over the X value. It's not changing by 0.8 days per parts per million. It's changing by 0.8 parts per million per day. It's kind of weird because the Y unit part per million has a per in it. So this Y value is actually a ratio. It's kind of cool. So again, I could say the concentration is decreasing by 0.8 parts per million per day, or I could say it's changing by negative 0.8 parts per million per day. Those would both be acceptable. All right, this last one is measuring the Houston metropolitan population. Now this 5E.06, that's something in scientific notation, which we have mentioned very, very lightly, and I mentioned that it's something you're supposed to study on your own. If you're in my MDE class, we did go over that because it's developmental or prereq material, however you want to call that. But that just means you take the 5 and you move its decimal right 1, 2, 3, 4, 5, 6 times. So there'd be 6 zeros. So that's y equals that number with the x plus 5 million. That's what that represents. If that's a negative, that means the decimal goes left 6 instead. Now, we don't even need that number for this problem. All we're doing is interpreting the slope. This is the intercept, or the fixed amount. So it has nothing to do with question, thankfully. But we will talk about it later. So the slope. We're talking about the growth of population. We're talking about the growth of the people, specifically for Houston. So the Houston metro population is changing by, or because it's going up, is increasing by. And then we write the slope, which is that 123,139. And then we do the ratio of the two different units. Well, we're talking about people and we're talking about years. Now, that doesn't just say years, it says years since 2000. That is going to be a very important distinction as we move forward. And I just realized I thought I had 7 minutes. I looked at my clock incorrectly. I am not that rushed for time. So, do we do years per people? Does that sound right? The population is increasing by years per people? No, that's not right. Writing the units in that order does not make sense. It's not for every one person increase, there's another 123,000 years. No, it's for every 1 year that goes by, there's that many more people. So it's people per year, question mark? Now, I've already pointed out that the fact that that thing says years since 2000, this is what ties together that whole mathematical models fall apart eventually side of things. This is how we prevent them falling apart for a while, at least, relative to where we are. If this just said that the Houston metro population is increasing by 120,000 people without the per year, that would not make sense when you look at the grand scheme of things. Because if you go back to, say, the year negative 3000 AD or 3000 BC, Houston didn't even exist. So from the year 3000 BC to the year 2999 BC, because they go down, did the population increase by 123,000 people? No, that's a horrible model. But if we only talk about things since the year 2000, since Houston has been established as a metro and is growing at a pretty consistent rate, then it can make sense. So just saying people per year, things get a little sketchy. But by saying people per year since some year close to us, that's how we can make population dynamics work a little better, whether we're talking about population growth, whether we're talking about dispersion of a virus amongst the population. We can have more accurate details when we look at a smaller time frame. That's how we make models actually work, by looking at a small time frame instead of a large time frame. Now, the idea of small and large depends on the type of model. Right now, we're dealing with linear models. We're going to graduate to exponential models eventually, and exponential models can look at a longer time frame. This model for the Houston population is probably going to fall apart in the next 10 years or so, this one that we're looking at. By 2030, it's probably going to slow down, or maybe it'll take off, but it's probably not going to stay consistent because people are dynamic. We change based on laws, based on things going on around us, whatever. So that's one of my favorite concepts, is how when we look at short time frames, one model is good. When we look at kind of medium time frames, another model that's a little more complicated is better. And then when we look at super long time frames, we're going to need a much, much, much more complicated model to deal with population dynamics. Now, when we're talking about a cost of something, models typically don't really change. When we talk about driving, if we're not accounting for pit stops and traffic, that model is not going to change. When we talk about people, something inherently is going to change at some point. Show me 2,000 years of history in which nothing changed, since we have become, what's the phrase I want to use? Indoor dwellers, I guess. All right, one more. And this one gets a little weirder. And we'll probably end up finishing it here today. Just looking at something else. Interpret the slope of the equation in real world terms. Same thing as before. We have our equation, which gives us the slope and the y-intercept, although I'm not talking about the y-intercept yet. Notice I said yet. We've got nice things labeled, dollars, monthly balance, and whoa, that's weird. Both the y-axis and the x-axis are talking about dollars, but they're talking about dollars of different things. One of them is dollars of a monthly balance in a savings account, and the other is the dollar amount of interest. So this isn't well labeled. It does say monthly interest here, so that's implied, but I would prefer that somewhere this says interest along that y-axis. And again, it is labeled here, so that's good enough, but if you want to be thorough, I'd label it here too. Now, this equation looks a little different than the other ones we just had, because this line isn't going all the way to the y-axis. It's not doing that. Also, I need to be clear that this right here, this line right here, this is not the y-axis in a traditional sense. It is the labeling of the y values, but it is not the traditional y-axis. And that's because this value right here is not 0. It's 16,200. So this graph is actually a zoomed in version of another graph. And what that graph would look like, if here's your 16,200, here's your 18,000. All right, we got interest amounts going at 82 for the 16,400, and then up to about 90. Is that 90? About 89. Something like that, roughly. Here is a much better depiction of the line, and I probably don't even have the x-axis long enough here. In fact, that's what I'm going to do. I'm going to erase that. I just want to make that look a little more accurate, because that's 2,000 right there. So yeah, we need to be all the way over here. That's much more accurate, much more accurate. So here's about 82, here's about 89, and even the y-axis is a little off, because if that's a distance of 7, that's still not very good. I need to start this over. Sorry. I'm trying to work with the space I've got. Let's call that 82. Let's call that 89. That'll be much better. Then here's our 16,200. Here's our 18,000. Sorry, it's getting a little ugly. This is a much better depiction if you want this to be 0 and 0 on the x and y axis respectively. That's what I mean by this picture right here is really a zoomed in picture of this model, this graph below, because this one does not have 0 labeled on the y-axis. This does not have 0 labeled on the x-axis. So these are not traditional x and y axes, which means if you trace this thing back to here and tried to call that the fixed amount, it's not the fixed amount, in fact, because it's not on the y-axis. You would have to take this one down here and trace this all the way back to the y-axis, and this is not drawn appropriately, but if I did draw it appropriately, it would end up going to here. And that would actually make sense, because interest is a product of your balance and time. Interest is just a product of your balance and time. Sorry, balance and rate. Time as well. but it's got all of them. Interest is PRT, principal times rate times time. The time aspect we will use sometimes we don't. We typically will not in here for reasons we'll explain in the next chapter. But interest is just a product of your balance times your APR, your periodic rate, whichever it is. That was stuff we talked about back in chapter 1. That's stuff you're supposed to have memorized by now. Yes, if you're talking simple interest over several years, you can throw in that time part, but our models don't use simple interest moving forward. So if you have a balance of $0, you should have an interest of $0 because $0 times whatever your savings rate is should be $0. So that's why if you actually look at the whole picture, it starts to make sense. Whereas here, it kind of looks like you'd think that's 0, 0, but it's not. It's like 16,200 gets you 81 bucks. All right, but the whole point of this was to write our equation, and we got to do that right now. I just wanted to make sure you understood you sometimes are given graphs that are not necessarily starting at an origin. The media loves to do this. It loves to try and confuse people because they can say, oh, well, this looks really bad. Well, I mean, it's not even the whole picture. You got to look at the whole picture to get a full understanding of it. So let me just rock my sentence right here. And we would say that the monthly interest is increasing, changing by something happened. The monthly interest is increasing by, now you use the slope, which is the number in front of the x, and I don't know why I'm pointing with my finger because I don't have the pen in my hand, 0.005, so by 0.005. Now that's measured in dollars. Interest is measured in dollars, so it's increasing by $0.005 per. Now you might say, well, the unit in the x value was dollars. But that just seems weird. It's increasing by $0.005 per dollar, whether you have the S or not. Well, you need to be a little more specific since these are both the same type of unit. Your interest is increasing by dollars based on a number of dollars of monthly balance. That's more well said. It's better said. The interest is increasing by $0.05 per dollar of monthly balance in the account. So $10 would get you 5 cents. $100 would give you 50 cents. $1,000 would get you $5. That's what this model goes to. We'll talk about this 2e to the minus 11 next time. We have essentially finished this section, so I am going to say that 5.2 is still due on the due date we had up originally at the beginning.
Which was November 9th. So again, we've got our 4.3, 4.4, 5.1, 5.2 My Math Lab homeworks. We've got our midterm. We've got our midterm review. Those are the things we should be working on. Remember, the midterm review will not be graded. You don't turn it into me. If you don't do it, that's fine, but I highly, highly, highly suggest that you do it because it'll help you prepare for the midterm itself. Per usual, if you have any questions, please shoot me an email. Besides that, please study hard, please work hard. Remember, TCC will have no classes on Tuesday, November 2nd due to Election Day, but that is still an active midterm day since we also have the first. Remember, I only have to give you 1 day. I'm being generous in giving you 2, so hopefully that's not an issue. Remember that you have to do the midterm in 1 sitting, but besides that, study hard, work hard, and we will see you next time. Take care, everybody.